Okay, so today we're going to talk a little bit about Module 4, Lesson 1. Module 4, at least the first 3 lessons, are going to be all about solving systems of linear equations. Okay, and what that means is that we're going to have two linear equations like this that are true at the same time. And we represent the fact that this is a system using these curly brackets over here on the side. That tells you that this system is true at the same time. And if we think back to what we've done in the past, we've graphed these linear equations before, right? And the reason why we call them linear equations is because the graphs are straight lines, right? And so we're looking for a solution that satisfies both of these equations at the same time. Okay, and what that means, since there's an x and a y in both of these, is the solutions are typically going to be ordered pairs. That'll be the most common situation. So I might ask you to decide whether uh, a point is a solution. Okay, and so if we are given a point and we just want to decide whether it's a solution or not, all we've got to do is plug it in to both equations and see if it works. You got to be a little careful here because, like, if I plug this into the first one, 3 plus 2 equals 5, well, it works, right? You don't want us to just say yes now, though, because it's got to satisfy both equations. And if I take this 3, 2, and I plug it in the other one, I get 16 equals 19, which is just not true. Okay. And so the answer to this question for that particular ordered pair would be no. Okay. But that's how we're going to check whether an ordered pair is a solution to a system. We're going to plug it into both equations. And if the answer is only yes, if it satisfies both equations, it gives you a true statement. Okay. So perfect example of why you have to be careful. Worked in the first one, didn't work in the second one. Okay. Now, we're more interested in being able to find that ordered pair if it exists for systems like this. So we're going to talk about what that's going to happen. But before we do that, before we get into the specifics of how we find those ordered pairs, let's talk kind of in general about what we expect. Now, we know that the graphs of both of these equations are going to be straight lines, right? And so the most common thing that will happen is, maybe you have one straight line that looks like this if we're talking graphically, and then the other straight line looks like this, maybe. Okay. And then the solution to our system is going to be this point where those two lines cross. And so in this particular example, which is by far the most common uh, thing that will happen when you have systems of equations, we have one solution at this ordered pair, right? Okay. We call this a consistent system because it has at least one solution, and an independent system. That means that there are two separate lines. So each of these cases that we're going to have is going to have a couple of words that we use to describe it. The word consistent means there's at least one solution to the system. And the word independent that we use here means there are two separate lines when we graph them. Now, this doesn't always happen though, right? There are a couple of other kind of special cases that we can come upon when we're working with these systems of linear equations. Another one would be, okay, my first line maybe goes like this, okay? And then my second line goes like this. Now, the word we use to describe these in math is that these lines are parallel. They're going at exactly the same slope, okay? And the key thing here, though, is with our system, our solution over here was the point where these crossed. Well, these are never going to cross. So this is one special case that we can run into here where there is no solution to the system. Makes sense because these lines are just never going to cross. So if we're describing this, okay, remember the word consistent means there was at least one solution, right? In this one, there are no solutions. So we call this an inconsistent system. Okay. Now there are still two separate lines here, right? So this is still an independent system because that's what that word means. There are two separate lines. So this system we would describe as inconsistent and independent. Okay. Now, one more kind of special case that we can run into, and this is more common than you would think, but it doesn't happen all the time. And our first line comes up here like this. Okay. And then our second line goes right on top of it. And so it ends up looking like just one line, or two lines are right on top of each other. Again, seems like it wouldn't happen very often, but it does happen a little more often than you would think. Okay. And so every point on this line is actually on both lines. Okay. And so we would say here that there are an infinite number of solutions for this particular system because every point on this line is on both equations. So every point on there is a solution. There's an infinite number of points in our line. Okay. So how would we describe this system? Well, there are definitely solutions, an infinite number of them, in fact. So this is another consistent system. Remember, the word consistent means there is at least one solution. Okay. But this line, there is not two separate lines. So we actually call this a dependent system. And that's kind of the word that we would use to describe this, is that the system is dependent. And that's everything that can happen. There are three different cases. We've got our one solution case here. We've got our no solution case here where our lines are parallel. And then we've got our infinite case here where our lines are right on top of each other. Okay, so there are actually several different methods that we're going to learn throughout this module for solving these systems of linear equations. But in this first lesson, we're really going to focus mostly on solving them graphically, which is not a method that most people would use to solve these, but the ideas behind this are going to be really important, especially if you take like a functions and modeling class with us. You're going to use the calculator to solve these kinds of things. And this is how we're going to solve it graphically. So understanding the ideas behind this are very important for going into a class like functions and modeling. Okay. But to solve these things by hand, what we have to do is we have to go back to our previous skills where we learned how to use to just graph these lines, right? Because that's what we're going to do. We're just going to graph these two separate lines kind of one at a time. So I'm going to look at this x plus y equals 9 equation first. And we have some choices for how to do this. Like a lot of people like to use the y-intercept form, and that will certainly work here. When I have a nice simple equation like this, I personally prefer to just use a table and the intercepts. I think it's quick and easy. So that's what I'm going to do here. I'm just going to take this line, the first one here. I'm going to set up a little XY table for it. And then all I'm going to do is I'm going to plug my zeros in, one for X, one for Y, get my intercepts for this graph. So if I'm going to plug 0 in for X, well, this just goes away, right? And so Y is equal to 9. Again, I'm not interested in looking at this equation at all just yet. I'm completely focused on the first equation for now, just graphing these one at a time. And then very similarly, when I plug 0 in for Y, this piece goes away. And so I've got X equals 9. And so I've got my intercepts. And remember, that's all we need to graph a line is an x-intercept or any 2 points, but an x-intercept and a y-intercept will work just fine. Okay. So now that I've got those 2 points, what I'm going to do is I'm just going to plot them on my graph over here. 2, 3, 4, 5, 6, 7, 8, 9. Out here is my x-intercept. And then up here is my y-intercept. And then when you're doing this by hand, it is very important that we're as precise as possible. So you will need to use a straight edge and some graph paper to get this to work out. Now, the nice thing about the way that we're doing this class is because we're doing it in my math lab, it's going to draw perfectly straight lines for you. So you won't have to worry about this too much, but it is important to understand if you are going to do something like this by hand, that you are pretty precise. You need to use a straight edge to go with this. So I'm going to do that here. And we'll see why here in just a second. Remember, what we're trying to do is we're trying to find the point where these two lines cross. And so precision is very important. So there's my first line drawn on my graph. Okay. So now I'm going to do the same thing for the second line. Again, I'm not worried about the first line anymore at all. I'm just focused on the second line. And again, I'm just going to set up a little XY table. I'm going to plug those zeros in. Okay. So if I plug 0 in for X, this one goes away, right? So I've got minus Y equals -1. To solve, I need to divide by -1 on both sides. So I'll get Y is equal to 1. Okay. And then for the second one, I'm going to plug 0 in for Y, makes this piece go away. And we just get X equals -1. And so -1, 0 is going to be my point on that one. Okay. So now that I got my table filled out, I'm just going to plot those points. 0, 1 is right here. -1, 0 is right here. And again, very important if we're going to do this by hand to graph these things as precisely as possible, because again, we're looking for where these two lines cross. Okay. Okay. And so as long as I've done a good job, I can find that point where these two lines cross. Okay. Okay, and so the solution to the system is just going to be at this point right here, which is 1, 2, 3, 4, 1, 2, 3, 4, 5. And so 4, 5 is the solution to my system. And of course, like we talked about before, we can check this, okay, by plugging it back in. So 4 plus 5 does give me 9. And 4 minus 5 does give me -1. And so it works in both equations. So these things are pretty easy to check. You can just plug them into both equations and make sure you get a solutions to both. Okay, so let's look at another system here and solve it. Now, this is going to be an example of one of those special cases I was talking about earlier. So it's going to look a little different when we get done. So let's get started here by just graphing the lines one at a time. So I'm going to do the first one here first. Again, if I want to, I can use the table and the X and Y intercepts, but just to show you, you can certainly use slope intercept form to graph these as well. If you remember that one, and if you prefer that, that will work also. And this first one is a good candidate for that because it's very easy to solve for Y. Like if I wanted to solve this for Y, all I would have to do is move the 4X over to the other side. So we'll add 4X to both sides here, get rid of those. And I've got it in slope intercept form, right? And if you recall, this is Y equals mx plus b. So this is going to be like my Y intercept. So if I wanted to graph this, I would just start down here at -4, 1, 2, 3, 4 on my Y axis, right? So right down here. And then my slope is 4, right? Which, we want to think of like a fraction. So 4 over 1 is going to be my slope. And so I can use that from here as long as I have 1 point to move to my next point. So I would just go up 4 and over 1, right? And that'll give me my second point that I need. And then again, the key thing here is to make sure we are being precise with our graphing. So grab my straight edge here and connect those up. Get something like this, right? So the important thing is that we graph the line. We can use all of the strategies that we've used previously in the course. You can use a table, get the intercepts. You can also put it in slope intercept form and graph it that way if you prefer. Either one of those works just fine. Okay. And so we're done with the first one. We're going to forget about that one now. Look at the second one instead here. For that one, I'm just going to use a table. It's fine to do that way too. So we'll just set up a little XY table. Put in 0 for X and 0 for Y. Okay. If you put 0 in for X, that one goes away. So we get 2Y equals -8. Divide by 2 on both sides. So Y is equal to -4. So 0, -4 is my y-intercept. Then I plug 0 in for y. This piece goes away, right? So I've got -8x equals -8. We divide by -8 on both sides. So x has got to be 1. So 1, 0 is going to be a point on my graph. And then when we graph these, 0, -4 is right here, and 1, 0 is right here. We get those same points, and so our line is going to lie right on top of each other. Okay, so this is what I was talking about earlier. It doesn't look like these two lines are the same. They look quite different, but they're really the same. This first equation multiplied by 2 and then rearranged a little bit will get you that second equation. Okay, so and since we did it to both sides, it's really the same equation, just kind of disguised a little bit, if you will. Okay, so two lines are right on top of each other. So this is one of those special cases we were talking about earlier. Okay, when our lines are right on top of each other, what that tells you is that you have an infinite number of solutions. Sometimes we say that's an infinite solution set. Okay, and then the words we use to describe that is this system is dependent. There are not two separate lines here. There's just one line, and consistent because it has at least one solution. In this case, it has an infinite number of solutions. Okay, but the most common word we would use to describe this system is that it's a dependent system. Okay. And, similarly, we could have that situation where we have the two lines that are parallel. That would give us no solution. Okay, so hopefully that's enough of a start on this lesson to get you going. Please don't hesitate to let me know if you have any questions going forward. I'm happy to help. So y'all have a nice day.